Well, today we're diving into a really revolutionary technology that is completely changing the game for lab accuracy and, most importantly, for patient safety.
It's the most important question, isn't it? When your doctor makes a diagnosis based on a lab result, we're all putting our absolute trust in the precision of that data. The whole system is built on that trust. But what if the very methods that are supposed to guarantee that accuracy, what if they have a hidden and pretty dangerous blind spot?
So, to kick things off, we're going to pull back the curtain on the way labs have traditionally done quality control for decades now. We're going to explore some of the built-in risks that, have just been accepted as part of the process, risks that can have a direct and serious impact on patient care.
Okay, this slide gets right to the heart of the problem. For years and years, labs have used what's called conventional quality control. Now think of this like a scheduled spot check. A lab might test an artificial control sample, say once at the start of a shift. If that passes, they just assume the instrument is good to go for the next 8, sometimes even 12 hours. And the problem is that massive time gap. Think about it. If a subtle error, like a reagent just starting to go bad, if that begins just 5 minutes after that morning check, it can go completely undetected for the entire day. And during that 8 to 12-hour risk window, hundreds of patient samples could be run, and every single one of those results could be wrong. This isn't just a theory, it's a major built-in flaw in the system.
Now, what makes this even more insidious is a concept called the commutability issue. It sounds technical, but it boils down to a very simple problem. Those artificial control materials that labs buy, they aren't real human blood. They're manufactured, stabilized substances designed to mimic it. And mimic is the key word here. They don't always behave exactly like a real patient sample inside the complex chemistry of an analyzer. So you can actually have a situation where the machine develops an error that specifically affects human samples, but when the artificial control is tested, everything looks perfect. The system gives a green light, creating a total false sense of security, while it's actively pumping out incorrect results for real patients. It's a critical and honestly a terrifying blind spot.
Let's get into the mechanics and see how this all builds into a fully functional process. Now, at the heart of PBRTQC, there are really two main algorithms, two main ways of doing the math. On the left, you've got the moving average. It's super simple. You take a block of patient results, maybe 20 of them, add them all up and divide by 20. But the big problem here is that one single extreme result, say from a critically ill patient, can yank that average way off target and trigger a false alarm. That's where the moving median comes in. It's a much more robust solution. Instead of averaging, it just finds the middle value in that block of 20 results. By focusing on the middle, it naturally ignores those extreme high or low outliers, giving us a much more stable and reliable picture of our instrument's performance. To make our calculations even more stable, even smarter, we use a technique called truncation limits. The best way to think about this is that we're putting blinders on the algorithm. We basically tell the system, hey, only pay attention to the patient results that fall within this typical expected range. By electronically filtering out those extreme highs and lows that are probably due to a real but rare clinical condition, we can focus the calculation purely on the stability of the instrument itself.
See, instead of a simple average, which can get totally thrown off by one or two extreme results, the system looks at the median. That's the exact middle value in a group of recent patient results. And this makes it incredibly robust. One very sick patient with a super high or super low result won't trigger a false alarm because the median just naturally ignores those extreme outliers on either end. It's this focus on the stable, middle-of-the-road data that makes the system so good at spotting a real shift in the instrument's performance.
All right, now for the really cool part. We've talked about the theory, but what does this actually look like in action? We are going to walk through a real-world scenario, patient by patient, and watch this system catch a hidden error the very moment it happens.
Okay, let's set the stage. We're monitoring serum sodium, which is a super common test to check your body's fluid balance. The lab has set up a simple rule for this. The block size is 5 patient results, and the moving median has to stay between 139.0 and 140.0. So the first 4 patient results come in, but the system just waits because it needs a full block of 5. Then, patient 5's result comes through. The system now has its first block. It finds the median, which is 139.0. That's right on the lower limit, but it's still acceptable. Status: in control. Now, as patients 6 and 7 come in, the block moves. The oldest result gets dropped, and the newest one gets added. The median is recalculated every single time, and as you can see, it's holding steady at a perfect 140.0 right within our control limits. So far, so good. Everything looks great.
But now, something happens.
Unseen by anyone, a subtle malfunction occurs inside the analyzer. A small positive bias has just been introduced. From this exact moment on, every single result the machine produces will be slightly higher than it should be. And remember, the conventional QC system? It's hours away from its next check. The only thing that can catch this is our real-time system.
And there it is. Patient 8's sample is analyzed and the result is 145, which is artificially high because of that hidden bias. A result like this could suggest a patient has severe dehydration. But is it real? The moment this result is generated, the PBRTQC system calculates the moving median for the newest block of 5 patients. And the answer? 141.0. This value is immediately flagged because it's higher than the upper control limit of 140.0. Instantly, an alarm is triggered. Status: out of control.
So how did the system do that so fast? Let's break it down. First, it formed its block with the last 5 results. Second, it sorted that set of numbers from lowest to highest. Third, it just picked the middle value, in this case 141. And fourth, it compared that median to its rule. Since 141.0 is greater than 140.0, bam, the alarm goes off. Now the most critical part is that testing is halted immediately. No more patient samples are run. The error has been contained within minutes of its starting, preventing a wrong result for patient 8 and protecting every single patient after them. That is the power of real-time detection.
This real-time capability, it just fundamentally changes the entire philosophy of quality control. It moves it from being a passive, periodic check to an active, continuous surveillance system. But, it's not as simple as just flipping a switch. Labs go through a really deliberate and rigorous process, analyzing months of their own historical patient data to tune the system perfectly to their specific patient population. This makes sure that it's super sensitive to real errors, but also really robust against false alarms.
So you might be wondering, does this new tech mean labs just throw out the old methods entirely? No, absolutely not. The most effective approach, and the one that leading labs are adopting, is called the hybrid QC strategy. It's not about replacement, it's all about enhancement. It combines the strength of both systems to create this multi-layered safety net that is just way more resilient than either one could ever be on its own. It's truly the best of both worlds.
So let's look at how this actually works. In this hybrid model, each system gets a very clear and distinct role. Conventional QC is used for verification. You run it at the start of the day or after you do some maintenance to get a definitive yes, this machine is ready to go. But once it's verified, PBRTQC takes over for continuous surveillance. It becomes this tireless watchdog that's monitoring every single block of patients all day long, and it closes that dangerous 8 to 12-hour gap. And if a PBRTQC alarm does go off, guess what the first step in troubleshooting is? You run a conventional QC sample to verify the error. They work in perfect synergy, constantly checking and balancing each other.
We've seen how PBRTQC can catch errors the moment they occur, and that right there is a massive leap forward for patient safety. But the evolution, it doesn't stop there. This real-time data stream opens up an even more incredible possibility. What if we could actually see an error coming and stop it before it even affects a single patient?
This is where we're headed. PBRTQC is really the foundation for a truly intelligent lab. There are already more advanced algorithms out there that can detect even smaller, more gradual drifts in an instrument's performance. But the real frontier is machine learning and AI. By feeding these powerful AI models the continuous stream of data that PBRTQC provides, we can build systems that don't just react to problems, they learn the unique personality of an instrument and can predict when it's about to fail. This is the future, a proactive, predictive, and ultimately a much, much safer laboratory, all built on the simple, powerful idea of listening to the data from the patients themselves.